Hello everyone and welcome to this EOMMasters mini tutorial, mini but mighty. There is often confusion about the difference between pixel size and spatial resolution. They are often considered the same, but that's not true. That's why we are going to look at the different resolutions used when dealing with Earth observation data. In fact, there are 4 different types of resolutions. The spatial resolution, the spectral resolution, the radiometric resolution, and the temporal resolution. From the photography, we know resolution as a number of pixels, either provided as x times y numbers or as megapixels number. Or when it comes to printing images or maps, we talk about DPI, dots per inch, but this is also something different. For Earth observation images, this is not very helpful. We want to know which details we can see. Often the term pixel size is used for this. Strictly speaking, this is not correct. Pixel size, or also called pixel spacing, is a distance on ground between the center points of 2 adjacent pixels. Now you might say, yes, this is a level of detail which can be seen in the image. Not necessarily. The level of detail is provided by the spatial resolution. Let me show you an example. Here you see 2 versions of a scene taken by the optical imager EOMMini on the Sentinel-2 platform. On the left with approximately 300 meter pixel spacing and 300 meter spatial resolution. On the right you see the same image but with a pixel spacing of 150. The spatial resolution is still 300 meter. Because I have simply changed the sampling and divided each pixel into 4, the spatial resolution, the ability to discriminate the details, has not changed. But the pixel distance has been cut into half. Often both values are quite close to each other. Especially for optical data, the commonly provided values for sensors like MODIS or EOMMini are only correct for pixels close to the nadir. As we get closer to the edges of the swath, the values change. In some cases, the pixel distance is corrected by adding duplicated pixels. But this does not correct the spatial resolution. For radar images, the spatial resolution is a special case and worth another EOMMasters mini video. Another value referring to the visual details of an image is a scale. It is used for maps and defines the ratio of distance on an image to actual ground distance. For example, 1 to 1000 means that 1 centimeter on the map is 1000 centimeters or 10 meters on the ground. Now coming to the spectral resolution. This type of resolution refers only to the passive optical sensors and defines the sensitivity of the sensor to the electromagnetic spectrum, from the visible light to infrared. We have multispectral and hyperspectral resolutions. Multispectral consists of a small number of bands, each covering a relatively broad frequency of the spectrum. There can be huge gaps between the single bands. For hyperspectral data, the number of bands is way higher, and the width of the bands is narrow, and there are only small gaps in the covered spectral range, if there are gaps at all. Here you see in the lower left a multispectral image of Sentinel-2, and in the upper left a hyperspectral image of EnMAP. Here on the right you see the spectrum of the Sentinel-2 image, and you see there are only few tie points. If I switch to EnMAP, you see the density of points is way higher, and even when I zoom in, the difference becomes even more obvious. Thinking again of photography, a grayscale image measures the intensity of the whole spectral bandwidth from 400 to 700 nanometers, roughly speaking. This represents the brightness. A RGB color image measures the 3 bands, blue, green and red, separately. Its spectral resolution is higher and we can see more information. Since you have watched this far, you seem to like the video. So please consider liking the video and subscribing to the channel. Thank you. The radiometric resolution refers to the sensitivity to the magnitude of the electromagnetic energy received by the sensor. It's the ability to discriminate slight differences in energy. This energy needs to be converted into digital numbers. If the recorded value is stored in an 8-bit digital number, there are 256 different values available. Measurements between two digital numbers are not considered and mapped to one of the numbers. The temporal resolution refers to the frequency at which a specific area is measured by a sensor, the revisit period. It is usually several days long. The temporal resolution is commonly given for areas at the equator. Areas closer to the poles have a lower revisit period value. They are observed with a higher frequency because the overlapping swath area of the orbits increase with increasing latitude. Let me quickly show you this. Here we have the swath, here, and the overlapping area is here smaller as closer to the pole. Here we have a higher overlap. Unfortunately, it is not possible to increase spatial, spectral and radiometric resolution at the same time. For high spatial resolution, the sensor must have a smaller instantaneous field of view to cover a smaller area on ground. In turn, this reduces the amount of energy that can be detected by the sensor. This leads to reduced radiometric resolution. To increase the radiometric resolution without reducing spatial resolution, it would be necessary to broaden the wavelength range detected by a particular band, and this would reduce the spectral resolution of the sensor. I hope this video could resolve some confusion about the different resolutions and we all can use the right terminology in the future. Thank you for watching. Tschüss and goodbye.